thank you to the organizers for continuing to bring the community together every year. So what I'll do is I'll talk about the damage spreading transition, which I think many of you in the audience are experts on, but I'll try to bring in a slightly new sort of angle to this problem. But before I start, let me just say that this work is on the archive. This is the reference, and this is sort of a longish paper, and I'm only going to present some parts of it. So if you're interested, please do look at that. And this was done in collaboration with Adam Nahum from ENS. All right, so what is the damage spreading transition? So the damage spreading transition is one of the most well studied and one of the most sort of prominent examples of non-equilibrium phase transitions in statistical mechanics. And at the heart of it, it's really an absorbing state phase transition. So to put it very simply, what you do is you take two copies or replicas of a dynamical system and you evolve them using exactly the same rules, but possibly different initial conditions. And when I say same rules, I should be even more sort of strict and say that if the system or the dynamics are noisy, then the same realization of the noise should also be applied on both the replicas. And once you do that, then you can ask the question, or by the way, damage is nothing but the initial conditions are different in the two replicas. And then you ask the question that does this damage or the difference in the initial condition survive for an arbitrarily long time, or do the systems actually heal? So the question is that, if you look at a very, very late time, do you still see the two replicas being different from each other in some way or the other? Or do you actually see that they are exactly, or their configurations or their trajectories have exactly coalesced on to each other? By the way, note that this is an absorbing state phase transition, because if the trajectories heal, namely, or if the systems heal, namely if the two trajectories ever become exactly the same with each other, then they'll continue to do so because the dynamical rules are exactly the same for all the replicas. Okay? So now we can ask this question that, what is the sort of underlying property of the rule that drives the transition? Now, to sort of say this in a way which we would like to present, let me give a very sort of simple example, and that's the example that we will be working with. So it's a square lattice, and we have Ising variables or bits on every side. They can take values 0 and 1. And what we have is a deterministic cellular automaton, which means that at every time t, these two qubits conspire together in some way to generate an output for this one, or rather these two generate an output for this one. Similarly, these two also generate an output for that one. And in principle, each of these rules can take in 4 inputs, because it takes in inputs as 2 Ising variables and can give out one of the 2 possible outputs. So now the point is that these rules can be maximally irreversible, by which I mean that this rule essentially has the same output for all the 4 inputs. Okay? And if you do that, then as you can sort of immediately understand, the 2 replicas are going to immediately collapse on top of each other. And that's basically the maximally irreversible setting. Of course, you can have another limit where the rules are partially reversible, namely that for 2 or 3 out of the 4 inputs, the output is different, or sorry, it's the same, and it's different for the other one. So of course, that tells me that there's a parameter p which tunes the mixture of the irreversible and reversible rules in the automaton, and that's what drives the transition. So you can already see one situation that if basically I have a very, very irreversible model, then it will heal. If not, then it might actually show a transition. Now, of course, I said that these rules are in terms of these spins, but you can, of course, write them down in terms of the damages themselves. And if you do that, you basically find something which has been very well studied, namely there is, so if 2 sites are healed, then of course they give you a healed site. If they're damaged, then they give you a damaged site with some probability p. And this exactly maps onto a directed bond percolation problem. And one way to see that is that you define a new problem on the dual lattice where a particular site of my earlier problem is now a bond. And if it is damaged, you say that it's a wet bond. If it's not damaged, you say it's a dry bond. And then this essentially becomes a directed percolation problem. And the critical point is known to a very high precision numerically. What we are now trying to say is that this is not the full story. And the main message of this talk is to basically say that damage spreading is much more there's a lot to it than directed percolation. And the simplest way to see that is you don't look at just 2 replicas, you look at multiple replicas. And once you do that, then you have to define many different kinds of damage operators. And these new damage operators are nothing but damages corresponding to different partitions. So each particular site on my system, it can happen that replicas 1, 3, 4, and 5 are in the same configuration, 2, 6, 9 are in the same configuration, and so on and so forth. And you can organize these damages in terms of these partitions. And our claim is that directed percolation captures only a small sector of the full theory, namely the observables, which can be expressed using 2 copies. Everything else is a different universality class. Okay, so here is a model. You don't have to look at this. I mean, this is exactly the model that we simulated. We basically said that each gate can take 4 inputs. It can give me 2 outputs. So this one is the maximally irreversible gate. These are the maximally reversible gates, and there are something in between. We have a parameterization of the model, and we exactly know where the phase transition is. But one thing that I should just add here is that you might just say that, well, we have Ising variables, so it can only be 0 or 1. So how do you actually put it in different partitions? That's very simple. We just say that we don't define operators or damages on single sites, but we define damages on multiple sites together. For example, we define a k-site operator in this way, which can take 2 to the power k values. And now if I'm allowed to take k4, I can easily handle up to 16 replicas and so on and so forth. This is actually not that important, but this is just a tool that we use to simulate higher and higher replicas. Okay, so now, as I said, you can define a damage operator for an arbitrary partition pi. There's one thing that one needs to be very careful about, and that is that all of these densities are not scaling operators. And we did a RG treatment, and what we showed that when you do an RG, then what happens is different damages actually get coupled to each other under the RG transformation, and then you have to block diagonalize the RG transformation to find out, you have to diagonalize the RG transformation to find out what your scaling operators are. One thing that happened, by the way, before we say that, this is, for example, a simulation. This is 3 replicas, so there are 5 possible partitions. This is basically a trajectory. Different colors are different damages. But one thing that you see is that I can compute the 2-copy operator by just appropriately taking sums. For example, I can ask what is the probability 1 is different from 2. So I have to add up 1 being different from 2, but 3 being the same as 2, or 3 can couple with 1, or all of them are the same. And this exactly looks like directed percolation, but these 3 directed percolation problems are not independent of each other. These are actually correlated with each other, and that's one reflection of the fact that the damages are actually coupled to each other. Now, one thing that happens is that for a given n, which is the number of replicas, the finest partition is a scaling operator that we can show, and that tells me that I can actually do calculations with that to see if there are new critical exponents. Now, this is a very brief sort of lightning review of how dynamical scaling works. You have a damage operator. You sort of say that at the critical point, the damage should decay like a power law, and then you have a correlation time scale, you have a correlation length scale, and you have another exponent delta n, which is often called the survival exponent. That's not actually important. So what we did was we simulated these models, and we found that with increasing n, you do see newer and newer critical points, critical exponents. The critical point is the same, and you do see newer and newer exponents, namely the alpha exponent and the delta exponent, which are the order parameter, and the survival probability exponents are different. And we also checked that, the other 2 exponents, they continue to be the same, and that basically gives us this full picture that with increasing n, 2 of the exponents change. For n equal to 2, these are the conventional directed percolation exponents. For the other ones, they are not. And that brings me to my conclusion. Let me just say that what I did not talk about is that you can do an analytic mean field treatment, and you do get different exponents with increasing n. And you can also do an RG and show the structure of the fixed points as they change with n. Okay, thank you.
Thank you, Sthitadhi. Time for a very short, quick question. If